There is a star in the constellation Libra that is older than the universe, not older than the Earth, not older than the Sun, older than the thing that is supposed to contain it. That is not a figure of speech. In 2013, an astronomer measured that star with the most precise instrument ever flown into space, and the number that came back was 14.46 billion years, in a cosmos we call 13.8. People went looking for the mistake. More than a decade later, nobody has found it. And when a new team listened to the star ring like a struck bell in 2025, it answered 14.2, still pressed against the ceiling, still refusing to be young enough. Tonight, you are going to find out why that star is not the real problem. The real problem is the clock we measured it against, a number that has been catastrophically wrong before, that two of the best minds alive now disagree about, at the level of certainty we reserve for Nobel Prizes. And that gets shakier every time we build a sharper telescope to pin it down. So get comfortable and subscribe or join if you have not already. If you want the wider map, the deeper walks through deep time, cosmology, and the places where physics quietly stops making sense, that all lives over on the Patreon. Stay to the end, because by the time we reach a galaxy that switched on less than 300 million years after the Big Bang, you will understand why no one can tell you, with a straight face, how old the universe actually is. Let's start where it started. In the spring of 2013, an astronomer named Howard Bond pointed the most precise pointing instrument ever flown into space at a dim, forgettable smear of light in the constellation Libra. The star has no name that anyone would recognize. It is catalogued as HD 140283, a string of digits from an old survey, and it is so faint that you could stand under the darkest sky left on this planet, let your eyes adjust for an hour, and never once find it. Bond was not looking for anything dramatic. He was measuring a distance. And when the measurement came back, and he fed it into the stellar models that have been refined and re-refined for the better part of a century, the number that appeared on the other side said this star was 14.46 billion years old. The universe is 13.8. The star, according to the best instruments human beings have ever constructed, is older than the universe that is supposed to contain it. Not by a little, by something close to 500 million years. A star with a birthday before the beginning. And here is the detail that should reach into your chest and stay there. The problem is not that somebody made a mistake. Mistakes get found. Mistakes get corrected. Quietly, in a follow-up paper, and everyone moves on. The problem is that this number got published in a real journal by serious people, and then a small army of other serious people went looking for the error, and more than a decade later, the error has not been conclusively found. The star is still sitting there in Libra, older than time, and the official response of the field has been to clear its throat and look at its shoes. I want to be careful with you, because you are not a child, and I am not going to lie to you to make this scarier than it is. There are ways to make the star younger. We are going to walk through every single one of them, slowly, with the actual numbers, because that is where this gets genuinely disturbing. But I need you to understand the shape of the thing before we climb inside it. The shape is this. A star appeared to be older than everything, and the response that should have happened, the one where we tear the foundations apart to find out why, did not happen. Instead, a much stranger move was made. We adjusted the star down toward the edge of what is allowed, parked it right against the ceiling, and called the matter closed. And the question I cannot let go of, the one this entire story turns on, is not how old that star is. You can argue about one star. One star can be a fluke, a bad parallax, a wrong assumption about how much oxygen is buried in its atmosphere. The question that should keep you here is the one underneath it. When that paper says the star is 14.46 billion years old, and the textbooks say the universe is 13.8, what is the 13.8? Where does it come from? Who measured it? How do they know? Because if you go looking for the answer to that question, the way I did, expecting to find some bedrock measurement, some single unimpeachable observation that pins the age of everything in place, what you find instead is that the number is not measured at all. It is assembled. It is the output of a chain of assumptions, and at least two of the links in that chain are right now, in 2026, openly at war with each other. The age of the universe is not a fact that we read off the sky. It is a settlement, and the settlement is starting to come apart. That is the real story. The star is just the door. So let me tell you about the door first, because it is a beautiful and lonely object, and it deserves better than to be a footnote in its own paradox. HD 140283 is what astronomers call a subgiant, a star a little further along in its life than our Sun, beginning the slow swell toward old age. It sits about 190 light-years away, which in cosmic terms is practically in the room with us. The light landing in Bond's instrument left that star around the 1830s, when the daguerreotype was new and nobody on Earth had ever seen a photograph of a human face. It is moving fast, far faster than the ordinary stars around it, tearing through our neighborhood at hundreds of kilometers per second on a long plunging orbit that does not belong to the flat disk of the Milky Way at all. It is just passing through. A visitor from the halo, the vast spherical cloud of ancient stars that surrounds the galaxy like a held breath. And it is almost entirely free of metals. When an astronomer says metals, they do not mean iron bars and copper wire. They mean everything heavier than hydrogen and helium, every element your body is built from. All of it. The Big Bang made hydrogen, helium, and a faint whisper of lithium and nothing else. Carbon, oxygen, nitrogen, the calcium in your bones, the iron in your blood, none of it existed in the first few minutes of the universe. All of it was forged later, in the cores of stars and in the fury of their deaths, and seeded back into space to be folded into the next generation. So the amount of metal in a star is a clock of a kind. A star drenched in heavy elements like the Sun, formed late, out of gas that had already been enriched by generations of stars that lived and died before it. A star with almost no metal at all formed early, out of gas that was still close to primordial, before the cosmos had time to manufacture much of anything. HD 140283 has roughly 250 times less iron than the Sun. 250 times. It formed out of gas that had barely been touched, gas only a step or two removed from the raw hydrogen and helium that came out of the Big Bang itself. This is a star that was present near the beginning, that watched the first galaxies assemble, that has been burning steadily and quietly while the entire visible history of the universe unspooled around it. Its discovery is older than you might think, too. It was first flagged as strange back in 1912 by the astronomer Walter Adams, who noticed that its spectrum did not match the kind of star it appeared to be. Decades later, in the 1950s, it became one of the first stars ever shown to be genuinely poor in heavy elements, a discovery that helped convince physicists that the elements really are cooked inside stars rather than handed down whole from creation. This faint smudge in Libra has been quietly informing our understanding of cosmic history for over 100 years. It earned a nickname. Eventually, people started calling it the Methuselah star, after the figure in scripture, who is said to have lived 969 years, the oldest thing anyone could think of. The nickname turned out to be a problem, because in the early 2000s, the team around Bond decided to do something that had never been done well enough before. They decided to measure exactly how far away it is, and distance, it turns out, is the whole game. If you do not know how far away a star is, you do not know how bright it truly is. And if you do not know how bright it truly is, you cannot place it correctly on the diagram that astronomers use to read a star's age. Get the distance wrong, and the age comes out wrong with it, dragged along like a shadow. The old distances to this star, from a satellite called Hipparcos in the 1990s, had error bars wide enough to drive a truck through. So Bond's team turned to the fine guidance sensors on the Hubble Space Telescope, instruments so precise they were originally built just to hold the telescope rock steady on a target. And over 11 separate observations spread between 2003 and 2011, they watched the star wobble against the background of more distant stars as the Earth swung around the Sun. That tiny wobble, the parallax, is the most honest distance measurement in all of astronomy. It is pure geometry. It does not depend on any theory of how stars work. It is just triangles. The wobble they measured was about 17 thousandths of an arcsecond. To give you a sense of that angle, it is roughly the width of a human hair seen from 10 kilometers away. And they nailed it to about 1 part in 100, which is 5 times better than anyone had managed before. With the distance locked down, they ran the star through the best stellar evolution models available, accounting for how a star of that mass and that pitifully low metal content would burn through its fuel, and out came 14.46 billion years, give or take 800 million. Take the give or take seriously, because it matters enormously, and I am not going to hide it from you the way a worse version of this story would. The headline number, 14.46, sits well above the age of the universe. But the uncertainty that 800 million years on either side means the star could in principle be as young as 13.66 billion years, which would scrape in just under the wire, or as old as 15.3, which would be a catastrophe. The error bar straddles the boundary, and Bond and his co-authors, to their credit, said so directly. In the paper itself, published in the Astrophysical Journal Letters in 2013, they wrote that within the errors, the age of the star does not actually conflict with the age of the universe. They wrote the responsible sentence. They put the fire extinguisher right next to the fire. But think about what that sentence is actually admitting. It is not saying the star is comfortably younger than the universe. It is saying that the best measurement we have lands the single oldest well-studied star in the sky directly on top of the age of the cosmos, with an uncertainty large enough that it could fall on either side. And we are choosing to assume it fell on the survivable side because the alternative is unthinkable. That is not a measurement that reassures you. That is a measurement that should make you ask how good our grip on any of these numbers really is. Because the only reason the star is allowed to be younger than the universe is that the error bar is wide enough to permit it. Narrow that error bar even slightly in the wrong direction, and the most famous reassuring sentence in this entire field stops being true. And here is the thing I promised I would not let slide past you. We have been here before. This exact situation, an object that appears older than the universe that holds it, with the establishment insisting the error bars will save us, is not new. It is not even unusual. It has happened, by my count, at least 3 separate times in the last 100 years, and every single time, the people who should have understood the universe best stood up in front of their colleagues and announced an age for the cosmos that was provably, embarrassingly wrong, sometimes wrong by a factor of 2. Once, gloriously, wrong in a way that made the universe younger than the rocks sitting in geology departments down the hall. So before we can decide whether the Methuselah star is a genuine crack in reality or just a measurement waiting to be tamed, you need to know something the popular science articles almost never tell you. You need to know the history of the number it is being compared against. You need to know where 13.8 billion years actually comes from, and how many times that clock has been smashed and rebuilt, and who fought about it, and who was ruined by it. Because once you understand how that number is made, the Methuselah star stops looking like an anomaly. It starts looking like a warning. The most precise instruments we have keep pushing our oldest objects right up against the ceiling of what the universe is supposed to allow, and they have been doing it, quietly, for a very long time. The clock has been wrong before. That is not speculation. That is the documented history of 20th century astronomy. And the question is whether it is wrong again right now, and whether this time we will be able to fix it, or whether the better our instruments get, the worse the disagreement becomes. It is the second one. I will tell you that now so you know where we are going. The better the instruments got, the worse it got. But to understand why that should genuinely frighten you, you have to go back to the man who started it all, and to the single most humiliating number in the history of cosmology. His name was Edwin Hubble, and you have a telescope named after him. The same telescope whose fine guidance sensors measured the Methuselah star, which is a small irony we will come back to. In 1929, Hubble published the observation that changed the size and the meaning of everything. He had been measuring the distances to other galaxies, which were only recently understood to be other galaxies at all, rather than smudges of gas inside our own, and he noticed that the farther away a galaxy was, the faster it was rushing away from us. The relationship was clean. Double the distance, double the speed of recession. It was the first direct evidence that the universe is expanding, that space itself is stretching and carrying the galaxies apart like raisins in rising dough. It is one of the foundational discoveries of the modern age, and it is taught, correctly, as a triumph. What is not taught, what gets very gently left out of the triumphant version, is that Hubble's number was wrong by a factor of about 7, and that the wrongness produced a result so absurd that it should have been a scandal, and somehow was not. Here is how the logic works, and it is worth slowing down for, because this exact logic is the thing that is broken today. If the universe is expanding, and you measure how fast everything is flying apart right now, you can run the movie backward. You can ask how long ago everything was packed together in the same place. That moment, when the run backward movie reaches 0, is the beginning, and the rate of expansion is the thing that sets the timescale. A faster expansion means the galaxies got to where they are quicker, which means less time has passed since the beginning, which means a younger universe. A slower expansion means everything took its time getting out here, which means more time has passed, which means an older universe. The expansion rate and the age of the universe are locked together like the two ends of a seesaw. Push one up, the other goes down. Remember that, because it is the hinge the whole modern crisis swings on. Hubble measured the expansion rate, the number we now call the Hubble constant, at around 500. The units are kilometers per second per megaparsec, which is a mouthful, but all it means is how much faster a galaxy recedes for every chunk of distance you add. 500. And when you take 500 and run the movie backward, the universe comes out to about 2 billion years old. 2 billion years. Now, in 1929, geologists had a problem with that, because by then, the radioactive dating of rocks was already maturing, and the oldest rocks on Earth were coming back at well over 2 billion years, and the Earth itself was clearly older still. Within a couple of decades, the age of the Earth would be pinned at 4.5 billion years, where it sits today, rock solid, one of the most secure numbers in all of science. The best cosmology of the early 20th century had produced a universe that was less than half the age of the planet you are standing on. The container was younger than the thing inside it. The stars and galaxies were comfortably older than the cosmos that held them. Does that sound familiar? It should. It is the Methuselah problem, the exact same shape, 80 years early, except worse. Because back then, the gap was not 500 million years sitting inside a forgiving error bar. It was a factor of 2, and the error bars did not save anybody. And the response of the scientific establishment to this absurdity was not panic. It was a kind of patient, embarrassed waiting, which is the response we keep seeing. Some astronomers quietly suspected the distance scale was off. Others wondered if the expansion law even held that far back. A few used it as ammunition against the whole idea of an expanding universe. Because if the expanding universe implied a cosmos younger than the Earth, maybe the universe was not expanding from a beginning at all. That last group included a brilliant, stubborn, magnificently wrong man named Fred Hoyle, who built an entire rival theory, the steady-state model, in which the universe had no beginning, was infinitely old, and quietly created new matter in the gaps as it expanded so it never thinned out. Hoyle hated the idea of a moment of creation. He thought it smuggled religion into physics. And in a radio broadcast on the BBC in 1949, reaching for a dismissive phrase to mock the theory he despised, the theory that the universe exploded out of a single point, Hoyle called it, with a sneer you can almost hear across the decades, the Big Bang. The name stuck. The man who coined the most famous term in cosmology meant it as an insult, spent his entire career fighting the thing he had named, and died in 2001 still not fully reconciled to it. And the cruelest part, the part the ultimate version of this story has to include, is that Fred Hoyle was also one of the people who worked out how stars forge the heavy elements in the first place. The same man who refused to believe in the beginning gave us the theory that lets us read a star's age from its metal content. The tool we use to date the Methuselah star was sharpened by the hand of the man who did not believe the universe had a birthday at all. The personal and the physical are not separate threads here. They are the same thread, running in both directions. But Hoyle was wrong about the steady state. And he was wrong because the distance scale was wrong. And the distance scale got fixed by a German Mieger named Walter Baade. During the Second World War, Baade was an enemy alien in Los Angeles, restricted in his movements, unable to do war work, which meant that while the other astronomers were off building radar, he had the great telescope on Mount Wilson almost entirely to himself. And the wartime blackouts of Los Angeles, which darkened the city sky for fear of bombing, gave him the clearest views anyone had ever had. Out of that strange luck, an enemy alien alone on a mountain under a blacked-out city, came the realization that there were two completely different populations of stars, and that the particular stars Hubble had used as his distance markers, the Cepheid variables, came in two flavors that nobody had distinguished. Hubble had been comparing the wrong kind to the wrong kind. He had gotten the distances badly wrong, which meant he had gotten the expansion rate badly wrong, which meant the age of the universe was badly wrong. In 1952, at a meeting of the International Astronomical Union in Rome, Baade stood up and announced the correction. At a stroke, the universe roughly doubled in size and roughly doubled in age. The cosmos went from 2 billion years to something more like 4 or 5, and for the first time it edged past the age of the Earth. The container was finally older than its contents. The room, by accounts, understood immediately what it was hearing. It was the sound of a paradox dissolving. And it should have taught everyone a permanent lesson about humility, about how the age of the universe is only ever as good as the shakiest distance in the chain. It did not teach that lesson, because the very next act of this story is two of the most powerful astronomers of the 20th century spending 30 years screaming at each other about a number and being unable to agree on it to within a factor of 2. The first was Alan Sandage, and you have to understand who Sandage was to understand the stakes. He was Hubble's hand-picked successor, the young man Hubble groomed to inherit the great program of measuring the universe. When Hubble died suddenly in 1953, the same year Sandage finished his doctorate, the entire enterprise fell onto the shoulders of a 27-year-old. Sandage spent the next half-century at the Carnegie observatories trying to measure the expansion rate of the universe with his own hands, and he became utterly convinced that the true value of the Hubble constant was low, somewhere around 50, which would make the universe large and old, comfortably more than 15 billion years. He was a difficult man. Colleagues described his temper as a force of nature. The physicist Wendy Friedman, who we will meet again, later recalled surviving what she called his verbal abuse. He treated the Hubble constant as something close to a personal inheritance, and he defended his low value with the ferocity of a man guarding a grave. And ranged against him was a French-born astronomer named Grade de Vaucouleurs, who was every bit as brilliant and every bit as stubborn, and who was equally convinced that the true value was high, around 100, which would make the universe small and young, possibly younger than 10 billion years. 100 versus 50. A factor of 2. For 30 years, these two men and their camps fought across the journals and the conference halls, each accusing the other of systematic errors, each refusing to give ground. And the result was that for 3 solid decades, anyone who asked the simple question, "How old is the universe?" got an answer that depended entirely on which of two feuding astronomers they happened to ask. The honest answer was that the age of the universe was uncertain by a factor of 2. Somewhere between about 10 and 20 billion years. Take your pick. I want you to sit with how recent that is. We are not talking about medieval astrology. The Hubble Wars, as they came to be called, raged through the 1970s and 80s and into the 90s. Within the lifetime of most people watching this, the single most fundamental number in cosmology, the duration of existence, was genuinely up for grabs by a factor of 2. And the disagreement was not polite. It was personal, it was bitter, and it was unresolved. I want to stay with Sandage for a moment, because he is the most human and the most tragic figure in this whole 100-year argument, and his story is the physics wearing a face. Picture the position he was put in. He was a graduate student, brilliant but young, when Edwin Hubble, the most famous astronomer in the world, the man who had discovered the expanding universe, chose him as his observing assistant and his heir. Hubble was grooming him to inherit the great program, to take the measurement of the cosmos into the next generation. And then, Hubble died of a stroke in 1953 suddenly, with the work unfinished, and the whole weight of it came down on a 27-year-old who had just finished his doctorate. Sandage did not ask to become the keeper of the age of the universe. It was handed to him, still warm, by a dying mentor, and he carried it for the rest of his life like a man carrying a relic he was terrified of dropping. And he came to believe, with his whole being, that the universe was large and old and slow, that the expansion rate was low, around 50, that the cosmos stretched vast and ancient, comfortably more than 15 billion years old. He spent decades at the great telescopes refining that number, defending it, building his entire scientific identity around a spacious, unhurried universe. The trouble was that he was, by every account, a difficult and combative man, prone to towering rages, who treated disagreement with his measurements as something close to personal betrayal. The astronomer Wendy Friedman, who would later be central to ending the war he was fighting, described surviving what she remembered as his verbal abuse. Colleagues spoke of his temper the way you speak of weather, as a thing to be planned around. He had inherited the most important number in cosmology from the founder of the field, and he was not going to let anyone take it from him. But someone tried for 30 years, and that someone was Grade de Vauquelins, a French-born astronomer every bit as gifted and every bit as immovable, who had concluded with equal certainty that Sandage was simply wrong. De Vauquelins put the expansion rate at around 100, twice Sandage's value, which would make the universe roughly half as old, small and young, where Sandage's was vast and ancient. And the two of them went to war, across the journals, across the conference halls, for 3 decades. They accused each other of systematic errors. They reanalyzed each other's data and published the reanalysis as rebukes. Younger astronomers learned to navigate the field by knowing which camp a given result came from. 2 brilliant men, each convinced the other was incompetent, each holding fast to a number that differed from the others by a factor of 2, neither able to land the blow that would end it, because the data of the era simply was not good enough to decide between them. The age of the universe, in those years, was not a fact. It was a feud. You did not look it up. You picked a side. And the cruelest irony, the one the careful version of this story has to name, is that they were both partly wrong. When the dust finally settled in the late 1990s, the answer came out near 72, almost exactly between their 2 warring values, closer to the midpoint than to either man's life work. Sandage's spacious, slow universe was too slow. De Vauquelins's cramped, fast one was too fast. Each had spent a career defending a position that the truth would split down the middle. De Vauquelins died in 1995, just before the resolution, still defending 100. Sandage lived longer, into 2010, and softened in some ways. He turned to religious faith in his later years and wrote about the harmony he found between science and belief, an unexpected gentleness from a man remembered for his fury. But he never fully surrendered his low number. His final published work still leaned toward a slower, older universe than the consensus had reached, keeping his side of the argument alive almost literally to the end. He died of pancreatic cancer, with the question he had inherited from Hubble still, in his own mind, not quite answered the way the field had answered it. Think about what that life adds up to. A man is handed the age of the universe by his dying mentor at 27. He spends 50 years and an ocean of anger defending a particular answer. The answer turns out to be wrong, though not as wrong as his rivals. And he dies, still arguing, having passed the unfinished question on to the next generation, exactly as Hubble passed it to him. The age of the universe is a relic that no one who has held it has ever managed to set down as solved. It goes from hand to hand, each keeper certain they have nearly pinned it, each one handing it forward a little different, but no more final than they received it. Sandage's whole tragic, combative, brilliant life is a single iteration of the pattern this entire story is about. The number does not get solved. It gets inherited. And this is the part where I have to correct something that the clean, triumphant version of the story would have you believe, because it is a misconception that lets people sleep at night, and it is wrong. The age of the universe is not measured. It is derived. There is no instrument anywhere that you point at the sky and read off 13.8 billion years the way you read a temperature off a thermometer. The age is a calculation, and it takes as its raw materials the expansion rate, the amount of matter in the universe, the amount of that strange repulsive energy we call dark energy, and the assumption that a particular model of cosmology, the one we call lambda CDM, is actually correct. Feed those ingredients in, turn the mathematical crank, and the age falls out the other side. Change any of the ingredients, and the age changes with it. The 13.8 you have been handed your entire life is not a rock. It is the answer to an equation, and the equation is only as trustworthy as its inputs and its assumptions, every single one of which has been wrong before. So the Hubble wars finally ended, and they ended in a way that should have made everyone permanently nervous rather than relieved. They ended because two things happened at once in the late 1990s. The first was that a major project using the actual Hubble Space Telescope, led by that same Wendy Friedman who had survived Sanderji's temper, pinned the expansion rate at around 72, splitting the difference between the two warring camps almost exactly down the middle. And the second was stranger and bigger, and it brings a new figure into the story, a young observer who in 1998 discovered something about the universe that made it possible, finally, for the oldest stars to fit inside it. His name is Adam Riess, and he is the most important person in this entire story, because he is the man who solved the age crisis once and then, 20 years later, accidentally broke it open again. Adam Riess was born in 1969. He did his undergraduate work at the Massachusetts Institute of Technology and his doctorate at Harvard. And in the late 1990s, he was a young postdoctoral researcher chasing a question that seemed almost suicidally ambitious. He wanted to measure how the expansion of the universe was changing over time. Everyone assumed it was slowing down. It had to be slowing down. Gravity is attractive. All the matter in the universe pulls on all the other matter, so the expansion that started in the Big Bang should be gradually breaking, like a ball thrown upward losing speed as it climbs. The only question was whether it was slowing down fast enough to eventually stop and reverse, or slowly enough to coast outward forever. Nobody anywhere doubted that the answer was somewhere on that spectrum from slowing to slowing. Riess, working in parallel with a competing team led by Saul Perlmutter, used distant exploding stars, a particular kind of supernova that always detonates with very nearly the same intrinsic brightness, as cosmic mile markers. By measuring how bright these supernovae appeared and comparing that to how fast their host galaxies were receding, the teams could trace the expansion rate back across billions of years. And in 1998, the data came back saying something that Riess initially assumed had to be an error. The distant supernovae were too faint. They were farther away than they should be if the universe had been expanding at a steady or slowing rate. The only way to make the numbers work was if the expansion of the universe was not slowing down at all. It was speeding up. Something was pushing the universe apart, overwhelming the inward pull of all its gravity, accelerating the cosmos toward a colder and emptier future. We call that something dark energy, which is an honest name in the sense that it is mostly an admission that we have no idea what it is. It makes up roughly 70% of everything. It lives in empty space itself, and its discovery won Riess, Perlmutter, and Brian Schmidt the Nobel Prize in Physics in 2011. I want to dwell on the moment of that discovery, because it is one of the few times in this whole story where you can actually feel a scientist's reality shifting under their feet in real time, and the documents survive to prove it. When Riess first reduced the supernova data in late 1997 and early 1998, the result that came out was not the result anyone wanted, including him. The distant supernovae were too faint, which meant they were too far away, which meant the expansion had been speeding up rather than slowing down, and his first instinct was not triumph. It was suspicion of his own work. He assumed he had made an error, a positive value for the thing he was measuring, the cosmological constant, the very term Einstein had inserted into his equations and then famously called his greatest blunder before removing it, seemed too strange to be real. Riess later described checking and rechecking, looking for the mistake, half hoping to find one, because the alternative was a universe with a mysterious repulsive energy woven into the vacuum, an idea that sounded less like physics and more like something you would be embarrassed to say out loud at a conference. In an email to a colleague during this period, he wrote something to the effect that the result was both exciting and very scary. because the data were pulling them somewhere no one was prepared to go. Two competing teams, his and Perlmutter's, working separately, suspicious of each other, both arrived at the same impossible answer at roughly the same time, which is the only reason either of them dared to believe it. The universe is accelerating. Empty space pushes itself apart. Nobody had predicted it, nobody could explain it, and it was simply, undeniably, there in the light of the dying stars. And here is what dark energy actually is, which is the most honest and unsettling part. It is a name for our ignorance. We can measure its effects with exquisite precision. We can tell you it makes up about 70% of the total content of the universe, that it behaves like an energy built into the fabric of space, that as space expands and there is more space, there is more of it, driving the acceleration ever harder. What we cannot tell you is what it is. There is no agreed physical explanation for it. The simplest version, the vacuum energy predicted by quantum theory, comes out, when you calculate it, too large by a factor with more than 100 zeros after it. One of the worst predictions in the history of physics. Off not by a little, but by an amount so vast it is almost funny. So we measure dark energy, we build our entire cosmology on it. We let it set the age of the universe, and we have essentially no idea what we are talking about. It is the largest component of reality, and it is a placeholder for a thing we have not understood. That is the stranger we invited in to rescue the age of the universe in the 90s. A 70% majority of all existence, summoned precisely when the numbers needed saving, that we still cannot explain a quarter century later. Now here is why that discovery matters for our story, and it is a piece of cosmic bookkeeping that almost nobody connects to the age paradox, even though it is the entire reason the paradox went quiet for 20 years. Dark energy makes the universe older. If you have a universe that has been coasting and slowing under gravity the whole time, you get one age. But if you have a universe that spent its early life expanding more sedately and only recently kicked into acceleration, then for any given expansion rate you measure today, the universe needs to be older to have reached this point. Dark energy buys you time. It adds billions of years. And when you plug dark energy into the model, the calculated age of the universe rises to something comfortably above the ages of the oldest stars and the oldest globular clusters. The clock and its contents finally agreed. Adam Riess, by discovering that the universe is being torn apart by an invisible force we cannot explain, simultaneously and almost incidentally rescued the age of the universe from a crisis that had haunted it since Hubble. The oldest stars fit. The container was older than its contents, with room to spare. Everyone exhaled. That exhale lasted about 15 years. And then Adam Riess broke it himself, because Riess did not stop measuring. He is, by temperament, a measurer. The kind of scientist who is never satisfied that a number is nailed down tightly enough. And through the 2000s and 2010s, he turned his attention back to the oldest and most basic measurement of all, the one Hubble botched and Baard fixed, and Sandage and Dvorkulers spent 30 years brawling over. He set out to measure the expansion rate of the universe today, the Hubble constant, more precisely than anyone ever had. His project is called JWST, and the method is a careful ladder of distances. Start with stars, whose distances you can get by pure geometry, by parallax, the same triangle trick that measured the Methuselah star. Use those to calibrate a class of pulsing stars called Cepheids, the same Cepheids Biade sorted out, whose pulsation rate reveals their true brightness. Use the Cepheids to calibrate those reliable supernovae, and use the supernovae to reach deep into the expanding universe and read off the rate. Each rung calibrates the next. It is meticulous, it has been checked and rechecked for decades, and by 2022 Riess and the JWST team had driven the uncertainty down to about 1 part in 70. Their answer was 73, more precisely 73.04, with an uncertainty of about 1. The expansion rate of the universe, measured directly by climbing the distance ladder rung by rung, is 73 kilometers per second per megaparsec. And that should have been the triumphant end of a century of work. Hubble's 500, refined down through Barday and Sandage and Friedman, finally pinned to within 1% or 2. Except for one thing, there is another way to measure the expansion rate of the universe, a completely independent way that does not use stars or supernovae or any distance ladder at all. And it gives a different answer. Not a little different. Different in a way that, the more carefully both sides measure, refuses to go away. The other method reads the expansion rate of the oldest light in existence, the cosmic microwave background, the faint afterglow of the Big Bang itself, released when the universe was about 380,000 years old and cool enough to become transparent for the first time. That light has been traveling toward us for almost the entire history of the cosmos, and it carries, frozen into its tiny temperature ripples, a detailed snapshot of the infant universe. A satellite called Planck mapped that light with exquisite precision, and from the pattern of those ripples, combined with the lambda CDM model, you can calculate what the expansion rate ought to be. The Planck collaboration published its definitive analysis, and the number that came out was 67.4, with an uncertainty of only about half a point. And from that same analysis falls the famous age, 13.797 billion years, give or take 23 million. That is where your 13.8 comes from. It comes from Planck, from the afterglow of the Big Bang, run through the standard model of cosmology. Now look at what we have. One method, the direct one, climbing the ladder of stars and supernovae through the nearby universe, says the expansion rate is 73. The other method, reading the afterglow of the Big Bang and projecting forward through the model, says 67. And remember the seesaw, the hinge this whole story swings on. A higher expansion rate means a younger universe. If the true value is 73, the way Riess measures it, then the universe is not 13.8 billion years old. It is about 12.5, maybe 12.6, more than 1 billion years younger than the official number. And if the universe is 12.5 billion years old, then the Methuselah star at 14.46 is no longer sitting safely against the ceiling with its forgiving error bar. It has crashed straight through the roof, a star nearly 2 billion years older than the cosmos. The reassuring sentence in Bond's paper, the one about how the star does not conflict with the age of the universe, was written assuming the universe is 13.8. Change the age of the universe to 12.5, the value Riess's direct measurement implies, and that sentence becomes false. The paradox does not just return, it becomes unsurvivable. This is the thing nobody put on a magazine cover. The disagreement between the two ways of measuring the universe's expansion has a bloodless name, the Hubble tension, and that name does a lot of quiet work to make it sound smaller than it is. Tension, as if it were a slight awkwardness at a dinner party. What it actually is two of the most carefully executed measurements in the history of science, each refined over decades, each cross-checked by independent groups, arriving at answers that cannot both be right and cannot be reconciled, about the most fundamental property of the universe there is. And when you ask how serious the disagreement is, the statisticians have an answer, and the answer has been getting worse every single year. In the language of physics, the seriousness of a disagreement is measured in sigma, in standard deviations, in how far apart two numbers are compared to how uncertain each one is. 1 or 2 sigma is noise, the kind of disagreement you shrug off. 3 sigma is interesting. 5 sigma is the threshold physicists use to declare a discovery. the level of certainty at which they announced the Higgs boson and the gravitational wave. By 2019, the Hubble tension had reached 4.4 sigma. By the Shu-E's measurement of 2022, it had crossed 5. The disagreement between the early universe number and the late universe number is now as statistically significant as the discoveries we hand out Nobel Prizes for. Except this is not a discovery of something. It is a discovery that two things we are certain about cannot both be true. And I know exactly what the reasonable, sane response to this is, because it is the response the entire field reached for, and it is the response you are probably reaching for right now. One of the measurements must have a mistake in it, some subtle error, some overlooked source of contamination, some systematic bias buried in one of the two methods. The distance ladder is complicated, full of rungs, and any one of those rungs could be slightly miscalibrated. The Cepheids could be contaminated by light from neighboring stars, making them look closer than they are. There has to be an error. And the beautiful, terrible thing, the thing that turns this from an academic squabble into something that should genuinely unsettle you, is that they went looking for the error with the most powerful telescope ever built, and they did not find it. They found the opposite. When the James Webb Space Telescope reached orbit, one of the first things Riess and his collaborators did was use its far sharper vision to re-examine the Cepheid stars at the bottom of the distance ladder, specifically to test whether crowding, the blurring together of a Cepheid with its neighbors in older, blurrier images, had been faking the result all along. If crowding was the culprit, Webb's superior resolution would clean it up, and the 73 would slide down towards 67, and the tension would melt away, and everyone could go home. In 2024, the results came back. The crowding hypothesis was not just wrong. It was wrong at the level of 8 sigma. Webb confirmed the Cepheid distances. Riess stated, about as plainly as a careful scientist ever states anything, that they could now rule out a measurement error as the cause of the tension with very high confidence. The better instrument did not heal the wound, it deepened it. And by 2025, the most recent Shores analysis had pushed the local value to around 73.5, and the significance of the disagreement towards 6 sigma. 6 sigma, and climbing. I have read the papers on both sides of this, more of them than is healthy, and I want to tell you something about the emotional texture of the literature, because it does not come through in the press releases. The people doing this work are not excited. They are not breathlessly announcing a revolution. There is a flatness to the way the tension gets discussed in the actual papers, a kind of careful institutional reluctance, because every one of these people understands what it would mean if it is real, and none of them wants to be the one who says it out loud. If the tension is real, if it is not a mistake hiding in either measurement, then it means the standard model of cosmology, the lambda CDM model that gives us the 13.8, is incomplete. It means there is some piece of physics operating in the early universe that we have not accounted for, something that changed the rate of expansion in a way our equations do not capture. And if our equations of the early universe are incomplete, then the age of the universe that those equations produce, the 13.797, is not a fact. It is a placeholder. It is the best output of a model we have direct evidence is broken. So watch what has happened to the question we started with. We started with one strange star in Libra that seemed too old. And the moment we asked where its supposed birthday, the age of the universe, actually comes from, the ground opened up. The age of the universe comes from a model. The model is fed by measurements. Two of the most important measurements now disagree at 6 sigma. The disagreement says the model is incomplete. And an incomplete model means the age it produces is not trustworthy. The Methuselah star is not the anomaly. The Methuselah star is a smoke detector going off in a building we have just discovered may be on fire in a room we cannot see. And the thing about that star, the reason it will not leave me alone, is that it is not the only smoke detector. When you go looking, the entire ancient population of the universe, the oldest stars and the oldest clusters we can find, is crowded right up against the same ceiling, as if the universe were quietly insisting it is older than we are willing to let it be. To understand why one weird star becomes genuinely frightening, you have to know that astronomers do not actually trust single stars very much, and they are right not to. A single star is a tangle of uncertainties. You have to know its distance, its exact temperature, its precise chemical composition, the subtle physics of how energy moves through its interior, and every one of those is a place for an error to hide. This is exactly why Bond's paper could write that reassuring sentence. One star, wide error bars, plenty of room to retreat. If the Methuselah star were the only object in the sky brushing against the age of the universe, you could file it under measurement noise and forget it, and most people have. But it is not the only object, and the others do not depend on the same assumptions, which is the part that should make the hair on your arms stand up. Scattered through the halo of our galaxy are the globular clusters, dense spherical swarms of hundreds of thousands of stars, packed so tightly toward their centers that if you lived on a planet inside one, the night sky would blaze with thousands of stars brighter than any in our sky. These clusters are among the oldest structures in the universe. They formed early in the first burst of cosmic star formation, and crucially, all the stars in a given cluster formed at essentially the same time out of the same cloud of gas. That makes a globular cluster a vastly better clock than any single star. Because when you have hundreds of thousands of stars all the same age, but with a range of masses, they age at different rates in a way the physics predicts exactly. Heavy stars burn fast and die young. Lighter stars linger. So at any given moment, there is a specific mass of star that is just now reaching the end of its hydrogen-burning life, just now turning off the main sequence, and that turn-off point marches steadily down to lower and lower masses as the cluster ages. Find the turn-off, and you read the cluster's age off the whole population at once, with all those hundreds of thousands of stars averaging out the noise that plagues a single object. What do the clusters say? There is a cluster called M92 in the constellation Hercules, one of the most ancient and metal-poor objects known. In 2023, a team led by researchers including the veteran cluster dating astronomer Brian Chaboyer published a careful new determination of its age, and the answer was 13.8 billion years, with an uncertainty of about 3/4 billion. 13.8. That is not near the age of the universe. That is, to the precision we can manage, exactly the age of the universe. A swarm of stars in Hercules that appears to have formed at essentially the same instant the cosmos became old enough to make stars at all, sitting right on the line, the way the Methuselah star sits on the line, the way everything ancient seems to sit on the line. And here is the detail in that M92 paper that I cannot stop thinking about, because it tells you exactly where the bodies are buried. The team was explicit that the dominant source of uncertainty in the age, accounting for roughly 80% of the entire error budget, was the distance to the cluster. 80%. Not the stellar physics, not the chemistry, not the models of how the stars burn. The distance. The same weak link that fooled Hubble, the same weak link Baard had to fix. The same weak link Bond spent 11 Hubble observations trying to nail down for the Methuselah star, is still, in 2023, the single largest source of doubt in our measurement of how old the oldest things are. We have been fighting the same enemy for 100 years, and we have not beaten it. Every age in this story, the star, the clusters, the universe itself, ultimately rests on knowing how far away things are, and we still cannot measure that well enough to settle the question. The clusters do not stop at M92. There is NGC 6397, dated in the early 2000s to around 13.9 billion years. There is M4, where astronomers used an entirely different and independent clock, not the turn-off of the living stars, but the slow cooling of the dead ones. When a star like the Sun finishes its life, it leaves behind a white dwarf, an Earth-sized ember of degenerate matter that simply radiates away its leftover heat and fades, predictably, over billions of years. The faintest, coolest white dwarfs in a cluster have been cooling the longest. So the dimmest ember tells you how long the cluster has existed. It is a completely different physics from the main sequence turn-off, vulnerable to completely different errors, and when it was applied to M4, it returned an age of around 12.5 to 13 billion years. Two independent clocks, two different sets of assumptions, the same uncomfortable answer. These objects are old. They are as old as the universe is allowed to be, and they keep refusing to be any younger. I want to slow down here, because the numbers in this story are so large that they go numb in your mouth, and a number you cannot feel is a number you cannot be properly disturbed by. 13.8 billion years. 14.2. The difference between them, the gap that the entire crisis turns on, is something like 400 million years, and you nod along as if that means anything, but it does not mean anything yet, not in your body. So let me build it for you. Take the whole history of the universe, from the Big Bang to this exact moment, and compress it down into a single calendar year. The Big Bang is the first instant of the 1st of January. On that scale, every second is about 440 years of real time. The Sun and the Earth do not form until late August or early September. The first complex life on Earth shows up in December. The dinosaurs go extinct on the morning of the 30th of December. All of recorded human history, every pharaoh and every war and every word ever written down, fits into the last fraction of the last second before midnight on the 31st of December. Your entire life on that calendar is far less than the blink of an eye. And the Methuselah star. The Methuselah star forms in the first days of January in the first week, while the universe is still raw and hot and almost without metals. It has been burning since the opening days of the cosmic year. The disagreement between 14.2 and 13.8, the gap that breaks the model, is a matter of whether that star lit up in the first hours of the 1st of January or in the last hours of the 31st of the previous December, on a calendar that does not have a previous December. That is the absurdity in human terms. We are arguing about whether the oldest object we can see was born just after the year began or just before it could have begun at all. And the way we even attempt to settle that, the way we read an age off a star, is worth understanding in detail, because the detail is where the whole thing is fragile. Here is what an astronomer actually does. They take a star, or better a whole cluster of stars, and they plot brightness against color, which is really brightness against temperature, on a diagram that has been the workhorse of the field for over a century. Stars burning hydrogen in their cores fall along a single track on that diagram, the main sequence, and where a star sits on that track depends on its mass. The heavy stars are hot and blue and brilliant and short-lived. The light stars are cool and red and dim and nearly immortal. A star spends most of its life sitting in one place on that track, steadily fusing hydrogen, and then, when the hydrogen in its core runs out, it leaves the track. It turns off. It swells and cools and migrates across the diagram toward the red giant branch. The mass of the star that is just now turning off tells you the age, because you know exactly how long a star of that mass can burn before its core runs dry. In a young cluster, only the heaviest stars have turned off. In an ancient cluster, the turn-off has crept down to stars barely more massive than the Sun, because everything heavier has already died. Find the turn-off point, measure the brightness of the stars sitting right at it, and you have the age. But here is the fragility, and it is the same fragility that has haunted this story from Hubble onward. To know how bright those turn-off stars truly are, the intrinsic brightness that the age depends on, you have to know how far away the cluster is. The brightness you measure is just how bright they appear, and a dim star nearby looks exactly like a brilliant star far away. Get the distance wrong by 10% and you get the brightness wrong, and you get the turn-off mass wrong, and the age comes out wrong, dragged off by the same bad distance that poisoned everything Hubble touched. This is why the M92 team said 80% of their error came from distance. It is not a side issue, it is the issue. The HD 140283 measurement was a heroic 8-year campaign with the Hubble Space Telescope for one reason: to beat down the distance error, because everyone involved understood that the age is only ever as good as the distance, and the distance is the thing we are worst at. And this is exactly why the Gaia mission was supposed to be the rescue. Gaia was built to do nothing but measure distances, parallaxes for more than 1 billion stars, with a precision that turns the old measurements into rough sketches. When Gaia turned its attention to the Methuselah star and to the nearby calibrating stars at the bottom of every distance ladder, the expectation was that the distances would finally lock down and the ages would follow, clean and settled at last. I have already told you what actually happened, but it bears saying again in this context, because it is the heart of the whole sickness. The better distances did not produce a clean age for the Methuselah star. They moved the uncertainty into the chemistry and left the star still pressed against the ceiling. And the better distances at the bottom of the cosmic ladder did not reconcile Riess and Friedman. They sharpened the disagreement and turned it into a fight about which kind of star to trust. The single greatest improvement in our ability to measure cosmic distances since the invention of the telescope arrived, and it did not calm the contradictions, it made them louder. Now I need to stop and correct something, because there is a version of this argument running loose on the internet that is wrong, and the way it is wrong matters enormously. You will find videos and articles claiming that the Methuselah star, or these ancient clusters, definitively prove that the Big Bang is wrong, that the universe is secretly much older, that mainstream cosmology has been exposed and is hiding the truth. That is not what the evidence says, and I am not going to pretend it does, because the audience this channel respects can tell the difference between an unsettling truth and a comforting conspiracy, and the truth here is far more disturbing than the conspiracy. Here is the actual situation. No single one of these measurements, not the star, not M92, not the white dwarfs, is precise enough to prove that anything is older than the universe. Every one of them has an error bar wide enough to pull the object back under the wire if you assume the most favorable values. That is what the defenders of the standard picture correctly point out. But sit with what that defense is actually saying, because it is not the reassurance it pretends to be. The defense is not that we have measured these ages precisely and found them comfortably younger than the universe. The defense is that we cannot measure these ages precisely enough to be sure of anything. The error bars are not a safety margin. They are a confession. They are an admission that our grip on the age of the oldest objects in the universe is so loose that an object could be older than the cosmos and we would not be able to prove it, and an object could be younger and we would not be able to prove that either. The thing keeping the Methuselah star from being a 5-alarm fire is not knowledge. It is ignorance. It is the width of our uncertainty. We are not safe because we understand. We are safe because we cannot see clearly enough to be sure we should be afraid. That is a very different kind of safe. And this is the second time the clusters have done this to us. which is the part that turns the pattern from a coincidence into something that looks almost deliberate. Go back to the middle of the 1990s, after Hubble and Baard, but before Riess and dark energy. In 1995, two astronomers, Michael Bolte and Craig Hogan, published an analysis in the journal Nature of the ages of globular clusters, and their best estimate came out around 15 to 16 billion years. Meanwhile, the expansion measurements of the day, before dark energy was discovered, before the universe was known to be accelerating, implied a cosmos somewhere between about 8 and 13 billion years old. The clusters were older than the universe, again by billions of years. For the second time in the century, our oldest objects had walked straight through the ceiling, and for a few years, in the mid-90s, the age crisis was a genuine, acknowledged emergency in cosmology, discussed in those exact terms, a real possibility that something was fundamentally broken. And then dark energy rode in and saved everyone, the way I told you, by making the universe older for any given expansion rate, lifting the ceiling just high enough that the clusters fit underneath it again. The crisis evaporated, the textbooks were rewritten, and the whole episode got smoothed over into a tidy story about how science self-corrects. But look at what actually happened, because the institutional autopsy here is brutal. The age crisis of the 1990s was not solved by measuring the clusters more accurately. It was solved by discovering a brand new, completely unexplained form of energy that comprises 70% of the universe, that nobody predicted, that nobody understands to this day, and whose only job in this particular story was to make the numbers stop embarrassing us. We did not resolve the paradox. We invented something vast and invisible to absorb it. And that should make you wonder what we are going to have to invent this time, because that is the pattern, and I want to name it explicitly, the way the ultimate framework demands, and the way the careful version of this story requires. The universe has now appeared older than itself at least 3 times in 100 years. With Hubble, when the cosmos came out younger than the Earth. With the globular clusters in the 90s, when they came out older than the expansion age. And now, today, with the Methuselah star and M92, and the white dwarfs all crowding the ceiling, while the Hubble tension threatens to lower that ceiling by more than 1 billion years. 3 times. And every time, the response of the field has followed the same script. First, deny that the problem is real, point to the error bars. Second, when the problem will not go away, wait, hope better data dissolves. Third, when it still will not go away, change something fundamental about the model, a new distance scale, a new form of energy, until the contradiction is absorbed and the textbooks can go back to printing a single confident number. Here is what should keep you up tonight. And it is the thing this entire story has been quietly walking toward since the first minute. Every single one of these ages, the star, the clusters, the universe, is downstream of the same disputed quantity. They all depend, in the end, on the distance scale and the expansion rate, the exact numbers that 2 independent methods are now fighting over at 6 sigma. There is no independent clock. There is no measurement of cosmic age that sidesteps the broken machinery. When the expansion rate is in question, every age in the universe is in question simultaneously, the oldest stars and the youngest galaxies, and the cosmos that holds them all, because they are all being read off the same ruler. And the ruler is the thing in dispute. We did not find one broken clock in a building full of working ones. We found that there is only one clock, that everything else is just a face on the same mechanism, and that the mechanism is making a grinding sound we have heard twice before. The first 2 times, we got lucky. A new distance scale, a new form of energy. The contradiction was absorbed and we survived to print the number again. The question that this story exists to make you feel The question I do not have an answer to, and neither does anyone else, is what happens the third time if there is nothing left to invent. And while the cosmologists argue over the afterglow of the Big Bang and the supernovae in the nearby universe, a new instrument opened its eye on the deep past, on the first few 100 million years after the beginning, the era when there should be almost nothing to see at all. We sent the James Webb Space Telescope to look at the dawn of the universe, expecting to find it nearly empty. We did not find it nearly empty. We found it already full, already built, already old, in a universe that had barely begun. The logic of looking deep into space is that you are looking back in time, and this is not a metaphor, but the plain mechanical truth of how light works. Light is fast, but it is not infinitely fast. So when you look at something far away, you are seeing it as it was when the light left, not as it is now. Look at the sun, and you see it as it was 8 minutes ago. Look at the Methuselah star, and you see the 1830s. And look at a galaxy 13 billion light-years away, and you are seeing light that left it when the universe was an infant. Light that has been crossing space for almost the entire history of the cosmos to arrive, tonight, in the mirror of your telescope. So if you build a telescope sensitive enough, you can watch the early universe directly. Not reconstruct it, not model it, watch it. See the first galaxies switching on. The James Webb Space Telescope, which reached its observing post about 1.5 million kilometers from Earth in early 2022, was built to do exactly this. Its enormous gold-coated mirror collects infrared light, which is what the light from the earliest galaxies has become after being stretched by billions of years of cosmic expansion. Its wavelength dragged out toward the red and beyond by the same expansion of space that started this whole story. Webb was designed, among other things, to look further back than anything before it, into the first few 100 million years after the Big Bang, an era astronomers call cosmic dawn, when the very first galaxies were supposed to be assembling. The expectation, built on the standard model, on the 13.8 billion year timeline, was specific and confident. The early universe should be sparse. The first galaxies should be small, faint, ragged little clumps of stars only just beginning to come together, because in a young universe there has simply not been enough time to build anything large. Gravity works at a finite pace. You cannot assemble a massive, mature galaxy overnight. The models predicted a thin scattering of infant galaxies, and astronomers waited to see them confirmed. That is not what Webb found. In 2023, a team led by Evo Lab published a paper in Nature reporting 6 galaxies in the early universe, around 500 to 700 million years after the Big Bang, that were nothing like the faint clumps the models predicted. They were massive. Some of them appeared to contain as many stars as the modern Milky Way, a fully grown spiral galaxy that took more than 10 billion years to build, except these had somehow done it in a few 100 million. Lab, describing the problem, said that if you added up the stars in the most extreme of these objects, the total mass seemed to exceed the entire amount of matter that should have been available to form stars in that region of the universe at that time. Read that again slowly. The galaxies appeared to contain more stuff than there was stuff to make them from. They were not just early. They were, on their face, impossible. Galaxies that looked like they had been built before the universe had finished delivering the raw materials. The objects became known, half affectionately and half nervously, as universe breakers, and the theoretical response was swift and sharp. An astrophysicist named Michael Boylan Colchin published an analysis, also in Nature, working out exactly how much trouble these galaxies posed for the standard model. His finding was precise and damning. To build the most massive of the lab galaxies that early, the universe would have had to convert its available gas into stars with an efficiency of around 99%. Nearly all of the raw material turned into stars with almost no waste. And that is not how star formation works anywhere we have ever looked. In the universe we can study up close, the efficiency is around 10%. Galaxies are messy and wasteful. Most of the gas is blown away or heated up or simply never collapses. To make these early monsters fit the standard timeline, you would need cosmic dawn to have been almost 10 times more efficient at building galaxies than anything in the modern universe. An assembly line running at a pace that nothing in our experience of how galaxies form can explain. And then it got further. Because Lab's 6 galaxies were estimates based on the colors of the light, and skeptics reasonably pointed out that you can be fooled by colors, that some of those objects might be closer than they looked, or might be powered by feeding black holes rather than vast populations of stars. The astronomers went and got the harder measurement, the spectroscopic redshift, the gold standard, where you spread the light into its full spectrum and read the precise stretching directly. And in 2024, they confirmed a galaxy called JWST Z14-0 at a redshift of 14.32, which places it less than 300 million years after the Big Bang. Less than 300 million years. If the universe is 13.8 billion years old, this galaxy is shining at us from when the cosmos was about 2% of its current age. The first few minutes of the cosmic year, if you compress all of history into 12 months. And it is not a faint little clump. It is luminous and surprisingly large, hundreds of light years across, far brighter and more developed than the models said anything could possibly be that early. The discovery paper stated, in the careful prose of the field, that these objects point to a population of luminous, massive galaxies already in place less than 300 million years after the Big Bang, with numbers more than 10 times higher than anyone had extrapolated from everything we knew before Webb. 10 times more than predicted. The early universe is not sparse. It is crowded, and it is crowded with things that look too old for their age. There is a phenomenon here that I find more unsettling than the sheer size of these galaxies, and it is the existence of the dead ones. You would at least expect, in the frantic early universe, that whatever galaxies exist would be furiously forming new stars, blazing with the light of constant creation. But Webb has found galaxies in the early cosmos that have already stopped. Quiescent galaxies, the astronomers call them, or quenched, or just dead. A galaxy studied by a team including Tobias Lucer, sitting at a time only around 700 million years after the Big Bang, had already built up a large population of stars and then shut off, its star formation extinguished, coasting on the light of stars that were already, by cosmic standards, old, to build a large galaxy and then have it live long enough to exhaust or expel its gas and die, all within 700 million years, is a sequence of events that needs time the early universe does not appear to have had. Other teams have found similar dead giants, more than 10 times more abundant than any model predicted. These are not just galaxies that formed too fast. These are galaxies that formed too fast and then aged and died. The entire arc of a galactic life compressed into a window that the standard timeline says was barely long enough to start. Now, I promised you I would be honest about interpretation. And this is exactly the place where honesty matters most, because the JWST story is genuinely contested, and I am not going to tell you it is settled when it is not. The mainstream view, the one most working astronomers hold, is that these early galaxies are probably not breaking cosmology. They are stress-testing our understanding of how galaxies form, which is a different and more local kind of physics than the age of the universe. The masses may have been overestimated, because some of that light may come from gas around feeding black holes rather than from stars. Star formation in the early universe may have been burstier and more efficient than we assumed, without requiring the full 99%. Some of the strangest objects, the little red dots Webb keeps finding, are a live and unresolved debate as we speak. In 2026, with no consensus on what they even are. The respectable position is that the early galaxies are a puzzle about galaxy formation, not a refutation of the timeline. I think that position is probably right, and I also think it is doing something slippery that you should notice. Watch the move carefully, because it is the same move every single time. When the Methuselah star came out too old, the answer was that the stellar models or the distance must be off. It is a problem with how we measure stars, not with cosmology. When the globular clusters came out too old in the 90s, the answer was first the error bars and then a new form of energy. Now, when the galaxies come out too old, the answer is that it is a problem with how galaxies form, not with the timeline. In every case, the anomaly is quarantined. It is declared to be a problem with some specific local physics, stellar models, distance scales, galaxy formation, anything at all, except the one thing they all have in common, which is that they are all telling us the universe contains things that look too old for the age we have assigned it. 3 completely different kinds of objects, dated by 3 completely different methods, vulnerable to 3 completely different sources of error, are all saying the same thing in the same direction. They are all saying the universe is older or its contents formed faster than the clock allows. And each time we explain away the messenger and protect the clock. At some point, the number of independent messengers, all pointing the same way, stops being a coincidence you can explain one at a time. At some point, you have to ask whether the thing they have in common, the clock, is the thing that is actually wrong. That is not a fringe thought. That is just refusing to look away from a pattern, because looking at it is uncomfortable. And the discomfort is the whole reason this information lives in journals and conference talks instead of on the evening news, because there is no clean way to say it. There is no press release that reads, "The foundational number of cosmology is contested at 6 sigma, and our oldest objects keep brushing against a ceiling we cannot pin down, and we have quietly invented vast unexplained entities twice already to keep the contradictions absorbed." That sentence does not fit on a magazine cover. So it does not get said, and you do not get told, not because anyone is lying to you, but because that truth is structurally inconvenient in a way that institutions are very good at not mentioning. And the most inconvenient truth of all, the one I have been circling this entire time, is the thing that should have ended the tension and instead made it worse. For decades, the reasonable hope was that all of these problems were problems of precision. The error bars were wide, the instruments were crude, and surely, when we built better telescopes and measured more carefully, the contradictions would shrink and dissolve, and the universe would make sense again. That is the most natural assumption in all of science. Better data resolves disputes. It has been the engine of progress for 400 years. We built the better instruments anyway. We launched Gaia to measure the distances to 1 billion stars with a precision Hubble never dreamed of. We launched Webb to see the early universe directly. We turned the most sophisticated machines our species has ever made toward these exact questions, fully expecting them to be the resolution. And what happened next is the part of this story that I genuinely do not know how to think about. The part that breaks the 400-year promise that better data heals disagreement. The better instruments arrived. And the universe got harder to explain, not easier. Start with the Methuselah star itself, because the story of what better data did to it is almost too on the nose. Bond measured its distance with Hubble in 2013 and got 14.46 billion years. Then the European Space Agency's Gaia mission, a spacecraft built for one purpose, to measure the positions and distances of more than 1 billion stars, with a precision that makes Hubble's parallax look like a guess, turned its attention to the same star and measured the distance again, better, and the new, more precise distance shifted things. It implied the star was a little more massive than Bond's models had assumed, and a more massive star burns through its fuel faster, which makes it younger. So you might think, good, finally, the better instrument pulls the star down to safety, the paradox dissolves, we can all relax. Look at where it landed. The revised estimates that followed, using the better Gaia data and updated models, scattered between about 12 billion years and 14 billion years, depending on exactly which assumptions you made about the star's oxygen content and internal mixing. 12 to 14. The more precise distance did not deliver a clean answer comfortably under the ceiling. It delivered a range whose upper half still sits right against the age of the universe, and whose exact value depends on chemistry we still cannot measure precisely. The better instrument did not resolve the star. It just moved the uncertainty from the distance to the chemistry, like pressing on a balloon. The bulge does not go away. It moves to where your hand is not pressing. And then, in 2025, something genuinely remarkable happened. The kind of thing that should have been the resolution, and instead became the strangest twist in the whole tale. A team led by an astronomer named Mia Lundqvist did something to the Methuselah star that had never been done before. They listened to it. There is a technique called astroseismology, the study of starquakes, in which you measure the almost imperceptible flickering of a star's brightness caused by sound waves resonating through its interior, the same way you could in principle work out the internal structure of a bell from the exact tone it rings at. The sound waves trapped inside a star are set by its mass and its internal structure and its age, so if you can detect the flickering precisely enough, you can weigh the star and date it from the inside, with a method completely independent of the distance, completely independent of the chemistry models, completely independent of every assumption that made the earlier ages shaky. Using the transiting exoplanet survey satellite, recording the star's brightness 20 times a minute for an entire observing sector, the team pulled the faint music out of the Methuselah star for the first time. And the age they measured, by listening to the star ring, by the cleanest and most independent method ever applied to it, was 14.2 billion years, give or take 400 million. 14.2. The error bar is half what Bond's was, which means the new method is more confident, not less. And the paper states, in the measured language of the field, that this age is in agreement with the upper limit set by the age of the universe within 1 sigma. Read that sentence the way you now know how to read it. It is the same sentence Bond wrote in 2013, 12 years later, with a better method and a tighter error bar, and it says the same thing. The star sits against the ceiling. The best, most independent, most precise measurement we have ever made of the age of this star puts it at 14.2 billion years, in a universe that is supposed to be 13.8, and the only thing keeping that from being a contradiction is that the error bar is just barely wide enough, by 1 sigma, to permit it. 12 years of better instruments, a completely new and independent technique, and the star is exactly where it always was, pressed against the limit, daring us to measure it just a little more precisely. There is a detail buried in that 2025 paper that almost nobody noticed, and it is the kind of thing that makes me trust the measurement more and sleep worse. When they analyzed the starquakes, one of the basic quantities they extracted, the frequency at which the star's oscillations are strongest, came out significantly higher than the standard scaling relations predicted. The prediction was around 537. The measurement was around 611. The relations that work beautifully for ordinary stars like the Sun do not quite work for this ancient metal-starved object. Even the new method, the clean one, the one that was supposed to settle things, found a small crack, a place where the standard physics does not quite fit this star, extending a known discrepancy into a regime where it had never been tested. I am not telling you that crack means anything cosmic. It probably means the scaling relations need adjusting for metal-poor stars, which is a mundane and honest conclusion. I am telling you that every single time we look harder at this object, we find one more small thing that does not quite line up, and that the small things have a way of pointing in the same direction, which is toward the star being slightly stranger and slightly older than the model wants it to be. So the star did not resolve. Now go back up to the cosmic scale, to the Hubble tension, and watch the same thing happen there, because this is where the breaking of the 400-year promise becomes undeniable. The hope, the entire hope, was that better instruments would converge the two measurements, that the early universe number from Planck, 67, and the late universe number from Riess, 73, would walk toward each other as the data improved, meet somewhere in the middle, and the tension would be revealed as the artifact of imperfect measurement that everyone assumed it must be. That is not what the better data did. As I told you, Webb confirmed the Cepheid distances and ruled out the leading explanation at 8 sigma, and the local value drifted up towards 73.5 rather than down towards 67, and the disagreement climbed towards 6 sigma. The better instrument did not close the gap, it hardened it. But here is the twist that turns the Hubble tension from a clean disagreement into something closer to an epistemic nightmare, and it involves Wendy Friedman again, the same astronomer who survived Sandiji's temper, who led the project that ended the original Hubble wars at 72, splitting the difference. Friedman has spent her career measuring the expansion rate, and she does not trust the Cepheids the way Riess does. She prefers a different rung at the bottom of the distance ladder, a method using the brightest red giant stars, which she considers cleaner and less prone to contamination. And when Friedman's team, the Chicago Carnegie Hubble program, applied their methods to the new Webb data and published their results in 2025, they got a value of around 70.4, with their own preferred method landing even lower. And Friedman stated plainly that based on these new measurements, using 3 independent methods, she did not find strong evidence for a Hubble tension at all, and that it looked like the standard model was holding up after all. Think about what that means for a moment, because it is genuinely vertiginous. We do not even have a consensus on whether the two clocks disagree. Riess looks at the Webb data and sees the tension confirmed and hardened towards 6 sigma, a near certain signal that the standard model is broken. Friedman looks at the same Webb data, runs it through her preferred methods, and sees a value low enough that the tension might not exist at all, and the model is fine. 2 of the most accomplished observational cosmologists alive, using the same new telescope, on the same fundamental question, cannot agree on whether there is even a problem. The disagreement has gone one level deeper than the numbers. It is now a disagreement about whether there is a disagreement, and the difference between them comes down to which stars you trust at the very bottom of the ladder, the Cepheids or the red giants, which is to say, it comes down once again after 100 years to the distance scale, to the same weak link that fooled Hubble and that Bardet fixed, and that dominated 80% of the error in the M92 cluster. We are still, in the most literal sense, arguing about how far away the stars are. We never stopped. This is the state of the question in 2026, and I want to lay it out flatly so you feel the full weight of it without any drama added or subtracted. The age of the universe is calculated from a model. The model's most important input, the expansion rate, is measured 2 independent ways that disagree by about 9%. Whether that disagreement is real is itself disputed by the leading experts. If the disagreement is real and the high value is correct, the universe is around 12.5 billion years old, and the Methuselah star and the oldest clusters are catastrophically older than the cosmos that contains them. If the low value is correct, the standard 13.8 survives, and the oldest objects just barely fit, by the width of an error bar. We have built the finest instruments in human history specifically to settle this, and they have not settled it. They have sharpened every measurement, and the sharper everything gets, the more clearly the measurements contradict each other. The better we see, the less the picture makes sense. I have spent an unreasonable amount of time inside this literature, and I want to be honest with you about what it has done to me, because the ultimate version of this story requires the narrator to admit when the material has gotten under their skin and this material has gotten under mine. I came into it expecting to find that the Methuselah paradox was a tidy little error, a story about how science self-corrects, the kind of thing you explain and resolve and feel clever about. That is not what I found. What I found was that the deeper you go, the less solid the floor becomes, and that the people who know the most about this are the least certain, not the most. The popular science version radiates confidence. 13.8 billion years, full stop, settled, move along. The actual literature radiates something much closer to controlled unease, a field full of brilliant people who have measured everything as carefully as it can be measured and arrived at a picture that does not close, and who mostly cope by focusing on their own narrow piece of it and not looking too hard at the whole. And underneath all of it, holding the entire edifice up, is a single number that two methods cannot agree on and that has been catastrophically wrong twice before. Everything you think you know about the age of reality is balanced on that one contested number. And the strangest part, the part I keep coming back to, is what all of these arguing methods, for all their disagreement, secretly agree on. Here is the consensus, hiding underneath the disagreement, and once you see it, you cannot unsee it. Planck and Riess, and Friedman's red giants, and the globular cluster turnoffs, and the white dwarf cooling curves, and the astroseismology of the Methuselah star all disagree, sometimes violently, about the specific numbers. But every single one of them is doing the same kind of thing, and that kind of thing is not measuring the age of the universe. It is measuring something else, a distance, a brightness, a flicker, a temperature ripple, and then feeding that measurement into a model and deriving the age as an output. Not one of these methods reads the age directly off the sky. There is no cosmic clock face anywhere with a hand pointing at 13.8. Every age we possess, for the star, for the clusters, for the cosmos, is the conclusion of an argument, the last line of a calculation that began with a measurement of something else entirely and passed through a chain of assumptions to arrive at a number. The age of the universe is not an observation, it is an inference. And the one thing all the warring camps agree on, the thing none of them would dispute, is exactly that. They are all inferring. They just disagree about the inputs. That is the move I find genuinely chilling, and it is the move the whole field is built on. We talk about the age of the universe the way we talk about the boiling point of water or the speed of light, as a measured constant of nature, a fact you could in principle verify with the right instrument. It is not that. It is a derived quantity, the output of a model that we have direct, published, 6 sigma evidence may be incomplete, taking as its inputs measurements that the leading experts cannot agree on. We have dressed an inference in the clothing of a measurement, handed it to school children as a fact, printed it in every textbook, and quietly left the contested machinery that produces it in the journals where you will never look. That is not a conspiracy. Nobody decided to do it. It is just what institutions do with inconvenient complexity. They smooth it into a confident number, because a confident number is teachable, and a contested inference is not. And the smoothing happens so gradually and so reasonably that by the end, nobody can quite say where the honest uncertainty went. And the proof that the machinery is shakier than the confident number suggests is in what cosmologists are actually doing right now behind the textbook to try to save the model. Because if the Hubble tension is real, if the early universe and the late universe genuinely measure different expansion rates, then the standard model needs a new ingredient, the way it needed dark energy in the 90s, and the candidates being seriously proposed in the literature are a tour of how desperate the situation has become. The leading idea is called early dark energy, a hypothetical extra burst of repulsive energy that switched on briefly in the first 100,000 years of the universe, changed the expansion rate just enough to reconcile the two measurements, and then conveniently switched off again, leaving no other trace. There is no independent evidence that it exists. It is proposed for exactly one reason, to make the tension go away, the same way dark energy itself was a stranger that arrived precisely when the numbers needed rescuing. Others propose modifying gravity itself, rewriting Einstein on the largest scales. Others, at the edges, propose that the fundamental constants of physics might not be constant across cosmic time, which would unravel far more than the age of the universe. Every one of these is, in the end, the same act we have performed twice before. Invent something new and invisible, something whose only job is to absorb the contradiction, and the moment it is absorbed, go back to printing the confident number. This is the third time. Hubble, then the clusters, now this. And I told you near the beginning that the question this story exists to make you feel is what happens the third time if there is nothing left to invent. We are watching the field reach into the drawer for the next stranger, the next early dark energy, the next 70% of the universe that nobody predicted. And the honest truth is that we do not know if there is one in there that works. The escape hatches that have been proposed all have their own problems. Early dark energy creates new tensions with other measurements, even as it relieves this one. Modified gravity struggles to match the rest of the evidence. We are, right now, in the middle of the third great age crisis, and unlike the first two, it has not yet been resolved. The better instruments are making it worse instead of better, and the rescue ideas are not obviously working. This is not history. This is not a solved problem I am narrating from a safe distance. This is the live, unfinished, Six Sigma fracture running through the foundation of cosmology as you listen to this, and the people standing closest to it are the ones who look most worried. Let me bring it back down to the star, because the star is where the abstraction becomes something you can hold. The Methuselah star is 190 light-years away. The light arriving from it tonight left during the 1830s. In the time that light has been traveling, the United States fought a civil war. The telephone and the aeroplane and the atomic bomb and the internet were invented. And your entire life and the lives of everyone you have ever known happened and will happen, all of it inside the span of a single one-way trip of that star's light across an astronomically trivial distance. And in all that time, with all the instruments we built, we have not been able to answer the simplest question you could ask about that star. How old is it? We have measured it with Hubble and with Gaia and by listening to it ring, and the answer keeps coming back at the edge of impossible. 14.2 billion years, 14.46, pressed against a ceiling whose true height we cannot agree on. The oldest well-studied star in the sky, and we cannot tell you whether it is older than everything or just barely younger, because the answer depends on a number that two of the best minds in the field cannot agree even exists as a problem. I want to correct one last misconception before we follow this to the bottom, because it is the one that the comforting version of the story leans on hardest. And it is the one that falls apart under the lightest pressure. The comforting version says that this is just how science works, that uncertainty is normal, that the error bars will tighten and the methods will converge, and in 20 years we will have a clean answer, and this will all look like ordinary scientific progress. And uncertainty is normal, and science does self-correct, and that is all true. But notice what that comfort quietly assumes. It assumes the disagreement is shrinking. It assumes we are converging. And the actual data of the last decade says the precise opposite. The tension grew from 4.4 sigma to 5 to 6. The better telescope hardened it instead of healing it. The new technique on the Methuselah star landed it exactly where the old one did, against the ceiling. We are not converging. For the first time in this 100-year story, the better instruments are increasing the disagreement rather than resolving it, and that is the thing that has no precedent and no comfortable explanation. The first two age crises were resolved by better data. This one is being deepened by it. And if better data makes the contradiction worse rather than better, then the problem is not that our instruments are too crude. The problem is that something in the model is wrong. And the sharper we see, the more clearly the wrongness shows through. So, we arrive at the bottom, at the implication that has been waiting since the first minute, and I am not going to soften it, because softening it would be a lie. You are handed a number, 13.8 billion years, as the age of the universe, the total duration of existence, the one fixed point you would think reality could offer you, the floor beneath every other fact. That number is the most contested quantity in cosmology. It is not measured, it is inferred. From a model we have strong evidence is incomplete, fed by observations that the leading experts cannot reconcile, propped up by error bars wide enough to hide a paradox, and by invented entities summoned twice before precisely to keep the contradictions from showing. The oldest objects we can find, dated by completely independent methods, all crowd against the upper edge of what that number allows, as if the universe were quietly insisting it is older than we will let it be. And every time we build a finer instrument to settle the matter gets less settled, not more. That is the situation. That is what the literature actually says, underneath the confident textbook sentence. You were given a fact. It was never a fact. It was a settlement, and the settlement is breaking down, and here is where it reaches you. Because so far this has been a story about stars and satellites and feuding astronomers, and you could be forgiven for thinking it stays out there, safely far away, a curiosity about objects you will never touch. It does not stay out there. The age of the universe is not just a number about the universe. It is the scaffold that every other date in existence hangs from. When you read that the sun formed 4.5 billion years ago, that the first life on Earth appeared around 3.5 billion years ago, that the first galaxies lit up a few 100 million years after the beginning. Every one of those dates is positioned against the cosmic timeline, measured backward from now along a track whose total length is the age of the universe. Shorten that track, the way the high expansion rate threatens to, and everything on it slides. The whole history of existence, the entire sequence of events that produced the carbon in your cells and the iron in your blood, the elements forged in stars that lived and died before the sun existed. All of it is dated against a clock we have just discovered we cannot read with confidence. You are made of timestamps that point back to a beginning whose date is in dispute. Think about what you actually do when you look up at the night sky. Now that you know this, you are taught to experience it as a kind of museum, a fixed and ancient gallery of objects with known ages and known histories, the comfortable furniture of a universe we have measured and understood. That is the feeling the confident textbook number is designed to give you. A solved sky. But that is not the sky you are actually looking at. The sky you are actually looking at is a collection of objects whose ages we infer from a model that is fighting with itself, lit by light that has been traveling for durations we calculate against a contested timeline. Arranged in a history whose total length is the single most disputed quantity in the science. The Methuselah star is up there right now, in Libra, 14.2 billion years old by our best listening, in a universe we call 13.8, and we do not know which of those numbers to trust, or whether the gap between them is a measurement error, or a crack in the model, or the third warning in a 100-year sequence of warnings we keep explaining away. You are not looking at a solved sky. You are looking at an open question the size of everything. I keep returning to the people in this story, because the ultimate version of it understands that the physics and the human beings are the same thread, and the human thread here is almost unbearable when you line it up. Edwin Hubble measured the expansion of the universe and got an age younger than the Earth and never lived to see it fixed. Walter Bahard fixed it alone on a mountain under a city blacked out for fear of bombs, an enemy alien who happened to have the darkest sky in America. Fred Hoyle named the Big Bang as an insult, fought it his whole life, and gave us the very nucleosynthesis that lets us date the stars that haunt the theory he refused to accept. Alan Sandage inherited Hubble's life work and spent 50 years and an ocean of anger defending a value that turned out to be wrong, dying of cancer in 2010 with the question still open. Adam Riess discovered the dark energy that rescued the age of the universe from one crisis, won the Nobel Prize for it, and then, by measuring too carefully to stop, reopened the crisis from the other side, and now stands at the center of a 6 sigma fracture he cannot close. Every one of them devoted their life to pinning down the age of everything, and every one of them, so far, has handed the question to the next generation still unanswered. Slightly worse than they found it. The error bars in a different place but never gone. That is not a story of science triumphantly converging on the truth. That is a story of the smartest people we have, across a full century, circling a number they cannot land on, while it quietly slips between their hands. And I think the reason this particular open question unsettles me more than the famous ones, more than the mysteries of consciousness, or the interior of a black hole, is that this one was supposed to be solved. This was supposed to be the easy part. The age of the universe is in the opening pages of every astronomy textbook, stated as flatly as the number of planets. A settled fact you learn before you learn anything hard. The hard questions are allowed to be open. We expect to be uncertain about dark matter and quantum gravity and what came before the beginning, but the age, the plain duration of existence, that was supposed to be locked down, a thing we knew, a place to stand while we puzzled over the rest. And when you pull on it, even that, even the flaw, even the one number we hand to children as bedrock, turns out to be an inference balanced on a measurement that two of the best minds alive cannot agree about, growing more uncertain as our eyes grow sharper. If we cannot confidently say how old everything is, after 100 years and the finest instruments ever built, then I do not know what we are entitled to feel certain about. The flaw was never a flaw. It was a number we agreed to stop arguing about, and now we have started arguing again. There will be a resolution someday, of a kind. There always is. Some new piece of physics will be proposed and tested. Some new ingredient will be added to the model. Early dark energy, or something stranger. And the two expansion rates will be made to agree, and the textbooks will be quietly rewritten, and a new confident number will be printed. And the children of the future will learn it as bedrock the way you learned 13.8. And the new number might even be right. But you will know something they will not. Something the confident sentence in their textbook will not tell them. The same thing it did not tell you. You will know that the number is an inference, not an observation. You will know that it has been catastrophically wrong before, more than once, and rescued each time by inventing something vast that nobody had predicted. You will know that the oldest objects in the sky spent a century pressed against the ceiling, refusing to be comfortably young. And you will know that for a stretch of years, right around now, the better we looked, the less we understood, and the most fundamental number in cosmology came quietly unglued while almost no one outside the journals was told. The Methuselah star is still there. It was there before the argument started, and it will be there long after the current version of the argument ends. It has been burning in the halo of the galaxy for something close to the entire age of the universe, by every measurement we have ever made of it, whichever number you trust. It does not know that it is a paradox. It does not know that its age has been measured and remeasured, and that each time the answer lands at the edge of impossible. It just burns, slowly, the way it has burned since before there were galaxies arranged the way we see them, since before the gas that became the sun had been forged, a witness to the beginning that we cannot quite read. We built a telescope and named it after the man who got the age of the universe wrong by a factor of 7. We pointed that telescope at the oldest star we could find, and it told us the star was older than the universe, and then it told us, when we looked closer, that it could not be sure, because the universe's own age was a number it could not pin down either. The instrument named after the man who was wrong measured an object that revealed we might still be wrong. That is not a coincidence the universe arranged, but it is the kind of pattern that once you see it, makes the confident sentence in the textbook sound less like knowledge and more like a held breath. So the next time you read that the universe is 13.8 billion years old, state it flatly. No error bar, no asterisk. The way it is always stated, I want you to hear what is actually underneath it. Underneath it are two measurements that disagree by 9%, and a fight about whether they disagree at all. Underneath it is a model that needs an invisible stranger to balance the books, and is reaching into the drawer for a third one now. Underneath it is a century of the smartest people alive getting the answer wrong, again and again, and a star in Libra that has sat against the ceiling the entire time, older than it is allowed to be, lit by physics we have not finished understanding. The number is not a fact. It never was. It is the current truce in an argument that has been running for 100 years, and the truce is breaking, and the better we see, the worse it breaks. We do not know how old the universe is. We thought we did. We were getting less sure, not more, the entire time we were telling you we were certain. And somewhere in the constellation Libra, a faint star that formed near the beginning of everything is still burning, still older than the cosmos says it can be, keeping a time that does not match the time we keep. It is not waiting for us to figure it out. It has no stake in the answer. It will burn the same whether the universe is 12.5 billion years old or 14, whether the model holds or breaks, whether we ever learn the truth or simply agree, one more time, on a number we can live with and call it knowledge. The light you would see from it tonight left in the 1830s. By the time the next measurement comes back, the next telescope, the next technique, the next confident answer that will not be the last one, that light will already be long past you, gone out into the dark behind your eyes, carrying a date we still cannot read.